Hi all, I am Atul. Today I am going to present on the topic polymorphism and tautomeric preferences in Phenobam and the utility of NLO response to detect polymorphic impurities. Okay, first we can look into the main contents that I am going to present. First, let me select the pointer. Okay, first, I am going to explain what is polymorphism, what are polymorphs that I am going to express. Then, how the polymorphs are detected, the different polymorphs, how we can detect which polymer is, which polymorphs is. That's a detection of polymorphs. And the third one is second harmonic generation, how this phenomena, how this method is applicable for the detection of polymorphs. And fourth one is polymorphism in Phenobam. Phenobam is a drug that we are going to discuss very deep, very thoroughly. Okay, polymorphism in Phenobam. And the fifth one, synthesis of the drug Phenobam. Okay, then the sixth one, intermolecular interactions and molecular packing in different forms. Then the seventh one, the next topic we are going to discuss, we will be discussing PXRD pattern of Phenobam, how to detect the polymorphs of Phenobam. Is it possible to detect using PXRD, that we will discuss in the upcoming slides. Okay. Then the next, simple harmonic generation response of various polymorphic mixture. And last one, summary. Okay, we can discuss what is polymorph or polymorphism. Polymorphism is a phenomena. What is this phenomena? Phenomena deals with, it's a existence of solid material in more than one form or in a crystal structure. Means one molecule can exist in different forms, different crystalline structure. Okay, that's how it can form polymorph, or it is similar to isomerism in molecules. Okay, I mean, how this molecule can form different structure. It is formed by, it is possible by rotation around some bonds. So you can see here, this is simply a molecule. This is not Phenobam molecule, this is the ROI. Its a common name is ROI and the IUPAC name is written here. Okay, this molecule, this ROI, this molecule has 7 polymers. I have pasted here the space group and the rotation around these angle, these bonds, these bonds. Okay, NC bond, this bond is represented as theta theta. This is just an example for a molecule that's showing polymorphism. Okay, you have to understand what is polymorphism. Polymorphism is a phenomena when one molecule can exist in different forms or a crystal structure. Okay, different forms in crystal structure. This is an example of one molecule that show polymorphism. Okay, the compound is ROI. It's a very important molecule. I have taken this from a research paper published by Dr. Sajesh P. Thomas. And moving on to the next slide. Okay, how we can detect these polymorphs? Polymorphs basically, it's a one compound that can exist in different forms. We have to detect these polymorphs. What are the different types of polymorphs in that present? How we can determine? What are the main methods we can determine the polymorphs? Okay, the presence of an undecided polymorphs in a bulk sample of a specific polymorphs is an issue of concern. It is very important in the field of pharmaceutical industry. Okay, the polymorphs. We have to identify. Means all the properties of the polymorphs are not identical. The molecular formula is identical, but the stability and the properties are entirely different. That is very applicable in the case of pharmaceutical industry. So detection of these polymorphs, that is very important in the case of pharmaceutical industry. Okay, you can see here in this figure, you can see here the polymorphs can be detected by so many techniques, that is vibrational spectroscopy, thermal analysis, nano indentation techniques, and PXRD techniques. Okay, the detection of minor polymorphic impurities means the amount of polymorphic sample, that is the detection is very important. That's a very practically challenging one. Okay, the detection of the quantitative detection is also means the sometimes the amount of one sample is very less. One sample in the sense the polymorphic sample. If we need, suppose a molecule has two polymorphs A and B, but A is very useful in pharmaceutical industry and the compound B is some impurity, is considered as an impurity. We have to identify whether the compound is a polymorph or B, and we have to detect B, and we have to eliminate that B from A. That is a application in pharmaceutical. That's very important in the field of pharmaceutical industry. The question in front of us, that means the problem we are facing is, can we detect the polymorphic impurities present in lower levels that we are not detected by PXRD and IR spectroscopy? Okay, I already mentioned that polymorphs can be identified by using powder XRD and IR spectroscopy. Okay, but is it possible, or can we detect if the impurity is present in very lower levels? That means the quantity is very small. Can we detect the polymorphs using PXRD and IR spectra? That is the main problem that we are facing. Okay, then we are going to find a solution for detection of small quantity of uh, polymorphic sample. Before that, we should know what is second harmonic generation, SHG. SHG is not symbol, it's a second harmonic generation. Okay, what is second harmonic generation? Second harmonic generation is commonly called a frequency doubling method. Okay, frequency doubling. Why it is called frequency doubling method? It is very simple, because frequency doubling means something doubled. What is doubled? The frequency is become doubled. Okay, suppose when we have a crystal, it's a non-linear crystal. Okay, that's a property that I will discuss later. Okay, it's a non-linear crystal. When a light having particular frequency, okay, I'm taking it as a omega. You can see here, when a particular light having frequency omega is fall on a non-linear crystal. Okay, non-linear crystal, the light comes out from the sample that means the transmitted light, or the light came out, has a frequency double that of the incident frequency. Okay, that property is called second harmonic generation. That phenomena is called second harmonic generation. Okay, then what is second harmonic generation? It's simple. When a light having a particular frequency falls on a non-linear crystal, okay, the non-linear crystal, then the emitted light has the frequency double that of the incident lights. Not only the double, the same frequency also emitted. Okay, that is called second harmonic generation. But why we are discussing here? Because it is only applicable in the case of this phenomena is shown by only non-centrosymmetric molecule. Okay, non-centrosymmetric molecule. The usage as a technique to probe. Why we are explaining this second harmonic generation here? This technique is useful to probe the structural purity of material if one of the impurities is non-centrosymmetric. Why it is non-centrosymmetric? Because centrosymmetric molecule does not show which property is second harmonic generation. Okay, that means if the impurity is a non-centrosymmetric material, we can do simple harmonic generation, and we can identify the presence of the impurity, non-centrosymmetric impurity. Okay, I already mentioned that the striking light has a frequency omega, and the emitted light has a frequency double 2 omega. Okay, then you might have thought that is it obey the law of conservation of energy? Because omega is falling on a crystal and it emitted as a double the frequency. That means, is there any energy conservation? You may have the doubt in your mind. Okay, that way I am asking the question, does the simple harmonic generation comply with the law of conservation of energy? The answer is yes, it is obeying the law of conservation of energy. How it is obeying the law of conservation of energy? When I suppose the molecule is in the ground state, when a frequency fall on the molecules in the ground state, it excited to the virtual level. Okay, here this energy difference is taken as omega. Then at the same time, some of the molecules were in the excited state. Okay, the molecules in the excited state, when the light is falls on the molecules in the excited state, it also gets excited to the another virtual state. Okay, then the molecules present in here, you can see here present the molecule present in the ground state excited to the virtual level, first virtual state, and the molecules also present in the virtual state also excited to the next virtual level. Okay, then the second virtual state, the molecules present in the second virtual level de-excited to the ground state. Then how it's de-excited to the ground state? By emitting 2 omega. Okay, that's why the emitted radiation has the frequency of 2 omega. Here the energy is conserved. Okay. Okay, then the second harmonic generation process is obeying what law of conservation of energy. Okay, this is what second harmonic generation. Okay, then what is the polymorphism in phenobam? What is phenobam? Phenobam, you can see here the IUPAC name of phenobam is I have shown here. Okay, I have shown here. Okay, then phenobam is an anxiolytic and antidepressant potential drug. Okay, it's a drug. Phenobam is simply it's a drug, and it has mainly two tautomers, and it show the phenobam drug show two tautomeric structures. It show tautomeric. It's an isomer. Simply, it's an isomer. What is the importance of this isomer here? We can see this is the first tautomer and this is the second one. This is a phenobam molecule. Okay, I have taken this from Mercury software. Okay, this structure, and this is simply the structure of phenobam, and it shows two tautomers, tautomer 1 and tautomer. The difference is in this tautomer 1, in the first structure, there is a bond, or there is a linkage between NHN bond. Okay, NHN interaction. Okay, here we can see NHO interaction. There is a competition between two interaction. What are the interaction? NHN interaction and NHO interaction. These are the two competing interactions in the polymorphs of in the tautomers of phenobam, which is more preferable, that we are going to discuss. Okay, which form polymorphs? Okay, which is the preferable isomer, tautomer? Okay, that we are going to we are going to discuss, and we are going to find also which one is the most preferable tautomer. Okay. Okay, let's wait. Okay, next we are going to how the phenobam is synthesized. Okay, first the laboratory synthesized sample of phenobam. The laboratory synthesized sample of phenobam crystallized from DMF water solvent as per the patented method is in a monohydrate crystalline form. This is the monohydrate crystalline form. This is the form 1. This is what we crystallize. There is a patented procedure, and using that procedure we synthesize a phenobam, and which is crystallized in a DMF water solvent. This is the form 1 form. The space group is also written here. This is a monohydrate crystalline form. From the form 1 crystal we synthesized, I have I have shown here the temperature and the conditions of conversion of form 1 to form 2. Form 2 is an intermediate phase, and form 2 is converted into an anhydrous form. That's the form 3. It's a space 2p is also written here, CC, and the it's basically a synthesis process, synthesis of phenobam. Okay, then the form 4 is generated from acetonitrile as a minor product along with the form 3. This is generated, this formed along with the form 3. Okay, this is generated from acetonitrile, okay, as a major product along with the form 3. Okay, then last we synthesize form 5. Okay, we have synthesized all the forms of phenobam. There are 5 forms of these are all polymorphs of phenobam. We have synthesized all the 5 forms. Okay, that's what we are discussing in this slide. Okay, simply the synthesis of phenobam. Okay, then in the before mentioning the synthesis of phenobam, we are facing a problem. There are two tautomers, tautomer 1 and tautomer 2. Which tautomer is going to form these polymorphs? That's a main ambiguity. Ambiguity means confusion we are facing. Ambiguity regarding the preferred tautomeric structure. Which is the preferred tautomeric structure? Okay. For solving the confirmation or ambiguity regarding the preferred tautomeric structure, we have taken a difference Fourier map. Okay, we have taken the difference Fourier map of both the tautomers, tautomer 1 and tautomer 2. The different Fourier maps of electron density were generated from the accurate single crystal XRD data of all forms. All forms. We have taken the single crystal XRD data and we generated the difference Fourier maps. You can see here, this is the difference for Fourier map, and from the difference Fourier map, all forms from the different Fourier maps, so all the forms, it is clearly show that the proton is associated with the ring nitrogen. Okay, the proton is associated with the ring nitrogen. This is the ring nitrogen. This is the Fourier map of which one? This is the second tautomer. Okay, the ring nitrogen, the proton is associated with the ring nitrogen. Okay, that is very clear in the difference Fourier map. The proton is attached with the ring nitrogen. You can see the previous slide. In this slide, in the first slide, the proton is not attached with the ring nitrogen. Okay, it is not attached with the ring nitrogen. This is attached with this nitrogen. Okay, but the tautomer 2, the proton is attached with the ring nitrogen. Okay, that we can see in the difference Fourier map. Okay, this is the overlay diagram, means the different forms of these are all from which tautomer? Second, tautomer 2. Okay, tautomer 2. How we can identify this one is the preferred tautomeric structure. This we can obtain from the accurate single crystal XRD data, and we took the we generated the single Fourier maps. Okay, from that we can conclude that the tautomer 2 is the preferred one. Okay. Okay, in the tautomer 2, I have already mentioned that there are two types of interactions in tautomers. Okay, in first tautomer is a NHN interaction, and the second one, it is NHO interaction. We are dealing with this tautomer 2. Okay, the tautomer 2 is exclusively preferred, giving rise to a short intramolecular NHO hydrogen bond that locks the molecular conformation. This is the intramolecular hydrogen molecule, hydrogen bonding within the molecule. This is the intramolecular hydrogen molecule. Okay, that's how why this is stable. That means this conformation is locked. Why this is locked? This is due to the NHO, intramolecular hydrogen bond. There is a two competing interactions in the tautomers, tautomer 1 and tautomer 1. In the tautomer 2, tautomer 1, it is NHN interaction, and tautomer 2, it's a NHO, intramolecular hydrogen bonding, intramolecular hydrogen bonding. This locks the molecular conformation. Okay, that's why tautomer 2 is the preferred tautomeric structure. Okay, these are the main dimers formed, means seen in the different forms. Form 1, it's a centric amide synthone. This is interlinked by water molecule. You can see here, this is a dimer. Simply, these are the dimers present in each forms, and you can see here, this is the form 5. Form 5 is also a polymorph. Here you can see here, this is there is an NHO interaction. This is the intramolecular. You can see here NHO interaction. Here NHO interaction means intramolecular hydrogen bond. That is, this is which tautomer? Tautomer 2. Okay, this forms here the two dimers are interlinked by water molecule. Okay, this is a hydrogen bonding. The hydrogen bond is formed between here. Okay, this you can also see here. Here also form N hydrogen bonding. This is the N, H, here N, and this is H, O, NHO hydrogen bonding. Here also form NHO hydrogen bonding. So these are you can see here, NHO chains constitute the major interaction supported by weak CHCl and CH pi interactions. This is how form 3 is formed, and this is the form 4 is a non-syndrome symmetric NHO dimers further linked by NHO. You can see here NHO interaction. Okay, NHO interaction. This is simply intramolecular hydrogen bonding. Okay, these are simply the dimers present. These are the how the dimers formed in different forms of different polymorphs in Phenobam molecule. Okay, Then the next problem we have to find, the problem we are facing is how we can differentiate each of the dimers. That is the main problem we are discussing in this paper. Okay, how we can differentiate each of the polymorphs, each of the polymorphs means, that's why we learned the topic second harmonic generation. Okay, before that I already told that there are so many techniques for detecting the polymorphs. Then we have taken the PXRD pattern of Phenobam 1. Okay, Phenobam 1 is very important in the field of pharmaceutical industry. It's from that is form 1 is a this is used in clinical trials. Okay, and form 3 is considered as the impurity present in the form 1. Okay, what we have done is just form 1 is mixed with form 3. Form 3 is considered as the impurity. We have to find which form is present in the mixture. Okay, that is the main problem we are facing. That's a challenging problem. Okay, that's why we have mixed form 1 with form 3. Form 3 is taken in different percentage weight. Okay, different concentration of form 3, that we have prepared the different mixtures of form 1 and form 3, and form 3 is taken in different weight. Okay, different weight, 3 percentage of form 3 and 5 percentage, 10 percentage. We have prepared these composition. Okay, and we have taken the we took the PXRD pattern. Okay, PXRD pattern, but the problem is the mixture showed no PXRD peaks corresponds to the impurity phase at these 2 theta values, the intensity versus 2 theta. When we plotted the graph, the impurity, there is no PXRD peaks corresponds to the impurity peaks. Impurity is form 3. Okay, third form. Okay, that's when the sample content is very, sample means the impurity content. Here the impurity content is very low, we can't detect using PXRD. So initially I told that this is, we can find the uh, uh, detection, we can detect the presence of polymorphs using PXRD, but here the sample amount of the sample is very low, amount of the compound is very low. That's why we can detect the presence of the impurity. Okay, and another technique, FTIR spectra, Fourier transform IR spectra analysis as well, did not yield any characteristic differences. Okay, using FTIR we couldn't find the detection. We couldn't find the presence of form 3. Okay, and form 1, then since form 1 transform into form 3, form 1 is transformed into form 3 upon heating. When we heat, form 1 transform into, I already mentioned that in the synthesis of phenobam, it is by heating in 90-degree, 80-degree. I told that by heating, form 1 transform into form 3. Here the impurity detection based on thermal analysis was not possible. How? Why it is not possible? Because form 1 normally transforms into form 3, though. That's why we can't detect the presence of one form. That's not practically possible, because one form changes into another form. That's not thermally stable. That's why we can't use thermal techniques. Okay, that's why PXRD pattern and powder XRD and FTIR and these thermal analysis techniques we can use for detection of small amount of impurities in the compounds. Okay, in the mixtures. Okay, then this is in this scenario, this is very significant. The second harmonic generation, that's phenomena is very significant. Okay, I already told that this the third form means I mentioned the third form is the impurity present in the impurity present with the form 1. Okay, form 1. Okay, form 3, the impurity form 3 has a property that crystallizes in a non-centrosymmetric space group, CC. Okay, CC is a non-centrosymmetric space group. Since it is non-centrosymmetric space group, it shows the property of second harmonic generation. Okay, second harmonic generation.
when the sample, the non-linear optical sample, when we fall on a when we fall or if when we fall certain radiation having particular wavelength falls on a sample, the emitted radiation has a frequency double that of incident radiation. Okay, when frequency doubles, the wavelength becomes half of the incident radiation. That's why I am writing here lambda is the wavelength is 1064 nanometer, and it's reduced to half of the incident radiation. Okay, okay, the form 3, why we are why simple harmonic generation is applicable in the case of phenobam, because the impurity has the property, or it has a it crystallizes in a non-centrosymmetric space group. Since it is crystallizes in a non-centrosymmetric space group, it is applicable, or it is it's obey the second harmonic generation property. The polymorph 3 polymorph, the third polymorph obey the property of not obey, it shows the property of second harmonic generation. Okay, it responds to second harmonic, this polymer responds to second harmonic generation. You can see here when the amount of sample is very low. Okay, when the amount of sample, this is a simple harmonic generation peak. Okay, when the sample is very small, it's a very the quantity of the sample, the third sample means the amount of the impurity is very low, we get a notable peak here. Okay, this is the when the sample amount of the sample is increased, we will get a higher peak. The standard reference used here is urea. Okay, the when we take the third form alone, that means 100% form 3, we will get the signal double that of the standard reference. Okay, ureas, we will get the signal by here. Okay, it's above the 150, but when we take 100 percentage form 3, we will get a signal above 300. Okay, that's why form 3 exhibits a form 3. Why form 3 has the property? It is a centrosymmetric space group. Okay, form 3 exhibits a notable high value of simple harmonic generation signal intensity. The intensity of form 3 is way about 2 to 3 times that of the urea. Urea is the standard reference. Okay, we are using in the simple harmonic generation intensity. Okay, that's why we can use this methodology in the case of Phenobam. Okay, for separation of these polymorphs from 3 can be separated from 1. Okay, then next this is the what main idea of this paper. Okay, simple harmonic generation can be applicable in the, it is only applicable when the impurity has the property, or impurity is a non-centrosymmetric space group. Okay, it's a non-centrosymmetric space group. And the summary, what we have discussed so far is, first we have discussed the two tautomers that exhibited the tautomers in the phenobam molecule, the preferences of intramolecular hydrogen bond over the NHN detects the tautomeric preference. Which tautomer is more preference? Tautomer 2. Why it is more preference? It has a intramolecular hydrogen bonding, NHO hydrogen bonding. Then the second point we have discussed, simple harmonic generation based methodology has been proposed as a simple means to detect a specific polymorphic impurity in bulk sample of API. API means it's a pharmaceutical ingredient. Okay, it's provided it's provided the impurity is simple harmonic generation activity, because this the sample should show, because the one of the impurity should show, which should show the what symbol centrosymmetry, one of the component. The component means the impurity should show the simple harmonic, should be active, simple harmonic generative active. Okay, then only we can apply this technique. Okay, this simple harmonic generation technique. In this example, the method is demonstrated to detect low level of impurity. Okay, this method is mainly used to detect the samples containing low level of impurity, which could not be achieved by conventional method. We can't find the impurities using conventional methods. So the methods requires a minor phase to be simple harmonic generative active, SHG active, considering the large class of APAs where polymorph impurity crystallizes in a non-centric or chiral space group. This could provide to be a useful test methodology in the pharmaceutical industry. Okay, simply it's one of the molecules is one of the molecule in the sense one of the components, that is impurity should be simple harmonic generate active, then we can apply this technique, simple harmonic generation technique. Okay, 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 that's it from my side. Okay, thank you.